Welcome to the MEMS analysis video on MEMS teardown analysis. MEMS analysis is an electronic materials laboratory. We have performed an extensive analysis on several MEMS. In this video we compare Abracon and Microchip MEMS oscillators. The parts compared in this analysis are the Abracon AMMLPAL and the Microchip DSC613RI2A, both purchased from Mouser. The Abracon package is 2 mm by 1.6 mm. The Microchip is available in several packages. The one shown here is a 2.5 by 2 mm 6-lead VFLGA, a very thin fine-pitch land grid array. X-ray imaging reveals a complex, though similar, internal structure with two levels of bond wires. Although the Microchip part is in a larger package, its controller die is significantly smaller. By the branding, the die are rotated inside the package. The bond wires from the die connect to gold-plated pads on the surface of the substrate. These are connected to the solder pads on the other side by vias. Regions of the metallization that were not gold-plated have been etched away during package opening or decap. The MEMS die are glued to the tops of the controller die. The MEMS look similar. The MEMS are of similar technology. Both controller die show Microchip branding. Using an infrared microscope, we can see through the surface of the MEMS and get a glimpse of the active cavity. With the top metal in place, we see how each resonator connects to the bond wires. Polishing away the metal traces and marking on top of the MEMS, we obtain a clearer view of the MEMS cavity. Focusing on the cavities, we can see the resonators. Cross-sectioning the Abracon before the circles, red line, and at the circles, blue line, we see the cavity and understand that the circles are through vias connecting to the resonator structures. The MEMS die is at the top and its lid is at the bottom. What appears as a set of eyes in the bottom right image is the intersection of two gold bond wires connecting the controller die to the package substrate. Here are some dimensions. In the Abracon, the MEMS die is about 100 micrometer thick, and its lid 70 micrometer. The depth of the cavity is 32 micrometer. The right image is from an electron microscope. We have lost the colors, but we can increase the magnification and find out the material composition of different structures. Let's find out what materials are used in this device. At location 1, the controller die is a silicon die. At location 2, we find the MEMS lid, and at location 3 the MEMS die, which are also made of silicon. Location 4, the encapsulant is a typical silica-filled epoxy with possibly a brominated fire retardant. Location 5 is silver epoxy attaching the MEMS assembly to the controller die. The bottom of the controller die is attached to the package substrate. At location 6 we find the solder mask of the substrate. At location 7 the controller die is attached to the substrate with a glue containing silica particles. Here we look at how the MEMS structures are connecting to the outside world. Location 8 is a via inside the silicon MEMS die. It connects the inside of the MEMS cavity to the outside world. Location 10 and its twin are part of a circular trench etched in the die and coated with silicon oxide. The remaining cavity, location 9, is filled with polysilicon. The purpose of the trench is to isolate region 8 connecting the internal MEMS structures to the top of the MEMS unit, where it connects to a bond wire. Location 11 is a layer of silicon oxide, a dielectric providing isolation on the top surface. Location 12 is aluminium connecting the inside of the MEMS to bond wires and to the controller die. Now, let us cross-section the microchip MEMS. At this location, we are not in the MEMS cavity. We see that the substrate has only 2 layers of metal. Looking at the die, we realize that this MEMS, capped with silicone, is also upside down and communicates with the controller via 3 bond wires instead of 5. The MEMS die is 100 micrometer thick and its lid is 75 micrometer. The controller die is 115 micrometer thick. The dielectric layer on top of the MEMS die is less than 2 micrometer thick. Now for the materials. At location 1, the controller die is a silicon die. At location 2, we find a silver epoxy die attach. Location 3, the MEMS lid, and location 4 the MEMS die, are also made of silicon. Location 5 is the encapsulant, a typical silica-filled epoxy with a brominated fire retardant. It's all very similar to what we saw in the Abracon part. We are now looking at the top of the MEMS die, at the location of a bond wire. The bond wire, marked as 6, is made of gold. The bond pad, 7, is aluminium. Layer 8 is a silicon dioxide layer on top of the MEMS die. Here we are looking at the bottom of the controller die which is attached to the package substrate. At location 9, the glue contains silica particles. At location 10 we find the solder mask of the substrate. Back to the Abracon, we have opened the cavity to look at the MEMS active structures. Left is an optical image and right an image taken with the electron microscope. The resonator elements are the bars that look like piano keys. The round structures are the vias transferring the electrical signal to the top to the MEMS unit and eventually to the bond wires. Each via is connected to resonator electrodes. The microchip is a smaller version of the Abracon. Left is an optical image and right an image taken with the electron microscope. The resonator element is simpler. There are only 3 piano keys. The round structures are the vias transferring the electrical signal to the top to the MEMS unit and eventually to the bond wires. One via is connected to the floating top plate and one to the bottom electrode. They each connect to a bond wire on top of the MEMS. The third bond wire is connected to ground. Would you like to know more about these devices? We have cross-section images of the resonator. Or would you have MEO analysis look at a different one for you? Contact us by email or by using the contact form on our website. Thanks for watching. Please subscribe to our channel.